Okay, picture this. You open your inbox, and right there at the top is a message promising you a free, all-expenses-paid vacation if you just click some highly suspicious link. You instantly know it's junk, right? But how on earth does your computer know? How exactly does an algorithm decide to just bypass your inbox and send that message straight to your spam folder? It sounds like a really simple yes or no question, but the mathematical journey to actually get that answer is surprisingly fascinating. You see, predicting if an email is spam based entirely on the number of spammy words it contains presents a really unique challenge for machine learning. So let's dive into this by looking at what we might already know. You're probably familiar with linear regression. It's a fantastic tool when you want to predict a continuous numerical value, like, say, figuring out exactly how many minutes it's going to take to drive to the grocery store. But trying to use a linear model to answer a strict yes or no question, yeah, that's where things totally fall apart. We don't need a continuous driving time here. We need a formal probability. We need a value strictly bounded between 0 and 1. 0 meaning there's absolutely no chance it's spam, and 1 meaning a 100% guaranteed chance it's junk. And for that, we need a completely different approach: logistic regression. Welcome to This Explainer. Today, our mission is to uncover the exact mathematical tricks that machine learning models use to make these probability-based decisions. We are going to demystify logistic regression and explore what I like to call the great squish. As you'll see, we're going to figure out how algorithms take unbounded, infinite numbers and beautifully compress them into a tidy, strict probability. Here is our roadmap for today. Number 1, the probability problem. 2, the sigmoid solution. 3, calculating the log odds. 4, log loss explained. And finally, 5, the need for regularization. Let's get right into it. Section 1, the probability problem. Linear models need limits. Let's just imagine for a second that we train a standard linear regression model to predict spam based on the number of spammy words. We feed it an email, and the model spits out a score of 0.62. Now, you might look at that and think, okay, 0.62, that feels like a 62% chance. The lower the value, the less likely it's spam, right? But here is the fatal flaw with that logic. Linear models are straight lines. They simply don't have boundaries. If an email has a massive, ridiculous amount of spammy words, that straight line will just keep going up and up. It might output a score of 5 or 10 or 50. And on the flip side, it could output negative 20. Neither of those are formal probabilities. I mean, you literally can't have a negative 20% chance of something happening. So the absolute crucial point here is that a linear model needs limits. Which brings us to section 2, the sigmoid solution, squishing the output. Enter the sigmoid function. This thing is an absolute mathematical hero. What's so elegant about this function is that it acts like a cosmic trash compactor. You can feed it literally any number in the universe, from negative infinity all the way to positive infinity, and it will beautifully transform that input into an output strictly between 0 and 1. It basically takes the straight runaway line of our linear model and bends it into this constrained, gentle S shape. Just looking at the numbers here brilliantly illustrates exactly what happens when we feed data through that function. Look at the extremes. If our linear model outputs a negative 7, the sigmoid squishes it all the way down to 0.001. As the input decreases toward negative infinity, the output gets infinitely closer to 0. But, and this is key, it never actually touches it. On the other end, an input of 7 gives us 0.999. As the input increases, the output approaches 1, but again, never quite reaches it. Right in the middle, an input of exactly 0 gives us exactly 0.50. Boom, a 50-50 probability. No matter how wildly large or small the linear input gets, the sigmoid function safely contains it. Moving right along to section 3, calculating the log odds before the squish. We can totally demystify this math by breaking the entire pipeline down into 3 highly digestible chunks. First, the model calculates the linear output, which we call z. Second, it takes that z value and applies our new best friend, the sigmoid function. And third, it simply outputs the final probability, which we denote as y prime. It's a really simple, elegant 3-step dance going from raw data straight to a neat percentage. Let's look at a concrete example of step 1 in action. Imagine our model has already learned some weights and a bias from our training data, and we're currently evaluating an email with 3 distinct features. The equation calculates our z-value, which, by the way, is also known as the log odds. We start with a bias of 1. Then we add our weights multiplied by our features. So that's 2 times 0 minus 1 times 10 plus 5 times 2. If you do that arithmetic in your head, 1 plus 0 minus 10 plus 10, you get a total z-value of exactly 1. The linear part of our model has looked at the email's features and spit out the number 1. Now for step 2 and 3, the real payoff. We take that log odds value of 1 and we pass it right through the sigmoid function. The math works its magic and out pops 0.731. We have successfully taken raw, complex feature data, run it through a linear equation, squished it with an S-curve, and arrived at a precise 73.1% probability. Aha! So, remember that email with 10 spammy words we talked about at the very beginning? When we run those specific features through a trained logistic regression model, the math calculates exactly a 69% probability of it being junk. We didn't just guess, we mathematically mapped the features to a precise, undeniable probability. Next up, Section 4. Log loss explained. Why squared loss fails. Now hold on, record scratch moment. Why can't we just use our old friend's squared loss here? Well, here is exactly why squared loss breaks down completely on an S-curve. Because the sigmoid function approaches its limits of 1 and 0 so incredibly gradually, the rate of change is not constant. When the input gets larger, the output gets painfully close to 1. An input of 5 gives 0.993. An input of 10 gives 0.99998. If we use standard squared loss to calculate the errors here, we would literally start running out of memory precision on our computers trying to track these microscopic differences. The decimal places just grow out of control as the model approaches the asymptote. To fix this decimal meltdown, logistic regression uses a brilliantly designed alternative called log loss. Instead of just measuring the raw distance from the data to the prediction, log loss returns the logarithm of the magnitude of change. This completely solves our memory precision issue. It allows the model to accurately calculate errors and penalize bad predictions on an S-curve without the math getting bogged down in endless tiny decimal places. And finally, Section 5, regularization, setting the guardrails. Remember how we just talked about the model pushing those decimals closer and closer to 1 or 0? Well, actually, scratch that being entirely a good thing. That asymptotic nature is actually a bit of a hazard. If left completely unchecked, especially when dealing with a large number of features, the model will constantly try to drive its loss to absolute 0. It will push its internal weights to extreme numbers just to get that perfect 100% or 0% confidence. And this leads to a massive risk of overfitting, where the model essentially just memorizes the training data but performs terribly in the real world. To prevent this, we have to introduce penalties for model complexity. Two very common solutions are L2 regularization, which mathematically penalizes extreme weights, and early stopping, where we simply halt the training process while the loss is still decreasing before it even has a chance to overfit. So, we did it. We've solved the probability problem, squished our numbers, calculated our log loss, and prevented overfitting. Our model proudly looks at an email and declares, there is a 69% probability this is spam. But that leaves us with one final, deeply real-world question. Is 69% actually enough to confidently throw that email into the spam folder? Or should we wait until we are, say, 90% sure so we don't accidentally delete a critically important message from your boss? That exact decision, where we actually draw the line in the sand, is called a classification threshold. And it proves that even when the math behind the scenes is totally flawless, how we choose to apply it changes absolutely everything. Definitely something to think about the next time you clear out your inbox.